lecture, and we are going to talk about testing of positive real functions. As I said, there were some mathematical concepts which you find, it appeared to me that you found a bit difficult. So, we will go over it again as a review. Our definition of positive real function, oh no, this is not the one. Our definition of positive real function is, well, we also assume that this is rational. So, it is n of s by d of s and is PRF if and only if two conditions are met, that is f of s is real for s real, and the second condition is real part of f of s non-negative for real part of s non-negative. This is the definition. From the definition itself, we showed simple examples of positive real functions. For example, examples are k, which is real and positive k. This is a positive real function. Ks is a positive real function. K by s is a positive real function, and you can see that these three elements correspond to resistor, inductor and capacitor. Okay, impedances of resistors, capacitors and inductors, or admittances. Okay. So, any combination of them, we also showed that sum of two PR functions is PR. Okay. So, any combination of them either in series or in parallel or parallel series would be PR, and for that we showed that if f of s is PR, f is PR, then so is 1 over f, and therefore parallel combination which consists of sum of two admittances is also PR. Okay. And then we showed, then we tried to motivate why we should study PR functions. We said that all DPIs, all driving point emittances of passive networks are PRFs, which we proved. We stated this is a theorem, and then we proved that all Z of S driving point impedance satisfies the property that Z of S is real for S real, and real part of Z of S is non-negative for real part of S non-negative. We proved that, and we also proved that if f is PR, then 1 by f is PR. Therefore, if Z of S is PR, 1 by Z of S, which is admittance, should also be PR. Okay. So, that was the second part of the study, and then we considered some properties, and this is where much of the difficulty arose. The properties of PR, first we we have already shown that if f is PR, then 1 by f PR. F PR means that 1 by f is PR, and then if f1 2 are PR, then so is f1 plus f2, but not f1 minus f2 necessarily. F1 minus f2 will depend on the relative values of real part of f1 and real part of f2 for the right half plane. Okay. But f1 plus f2 is definitely PR. In terms of a circuit, it means series combination or parallel combination of two elements or two positive real functions. Okay. The third property we stated that poles and zeros, now zeros are included, poles and zeros of PR functions must be in left half plane, because right half plane will lead to instability and therefore a violation of the real part condition. Poles and zeros should be in left half plane, and then we allowed simple poles on j omega axis. If there are poles on j omega axis, they must be simple with real positive residues, and there were considerable discussion on this business of residues. Okay. First, what is a residue? Any rational function when expanded in partial fraction would be of the form, let us say ki divided by s plus si. What do I mean by pole on j omega axis? That is, in the S plane there exists a point, one or more points at which the function blows up, that is the function becomes infinity. This is the pole j omega 0, which means that if I write f of s as n of s by d of s, then d of s has a factor s plus j omega naught and necessarily s minus j omega naught, and therefore at s equal to j omega naught or minus j omega naught the function blows up, and that is a pole. Did your question have any other implication?
J omega naught, so it will have a factor of s plus omega naught.
That's right. If s plus j omega naught is a factor, s minus j omega naught should also be a factor, because the function has to be real for s real. And so this is one of the poles, the other pole must be here. Okay. Now if there exists a pole on the j omega axis, then this pole must be simple and the residue there must be real and positive. What is a residue, someone asked yesterday. Now I suppose that should have been done in signals and systems, but all right, we will consider this. Okay. We have an f of s which is equal to n of s by d of s, a rational function, and you know that any polynomial of degree n shall have n number of roots, and therefore I can write this as s plus si continued product over I. All right. There may be a some constant, let us say some constant k. The denominator can be factored into n number of roots. If the degree of d of s is small n, it can be factored into so many roots, and this then can be expanded in partial fraction. That is, I can write this as sum ai divided by s plus si summed up over I. Okay. The form that I have written here shows simple poles, but there may be multiple poles also. In other words, s plus si could be raised to the factor to the power pi, let us say. Okay. There can be multiple poles, but it suffices to as far as the definitions are concerned, it suffices to consider simple poles. If there are multiple poles, let us say at sk, then I shall have factors of the form, let us say b1 divided by s plus sk plus b2 divided by s plus sk whole squared. If there is a double pole, then I shall have two terms like this. If there is a triple pole, then there will be three terms like this, and so on and so forth. Okay. Now these constants ai which occur in the numerator are called the residues, and the reason is the following. Why they are called residues is that if you want to find out this constant ai, what you do is you multiply both sides by s plus si, multiply f of s and put s equal to minus si. What remains on the right hand side? Just ai. Isn't that right? All other factors multiplied by s plus si, put s equal to minus si, shall vanish. And this is one physical meaning of residue. That is what is left. Now residue in the complex variable has a slightly different intonation, which you do not wish to enter into. For our purpose, it suffices to say that these are the constants which occur in the numerators of the partial fraction expansion. One can ask at this stage, what would you do if you have multiple pole? Let us say sk is a double pole, there is a double pole at sk. Then there are two residues, b1 and b2. b1 is called the first order residue and b2 is called the second order residue. Obviously b2 can be found out by multiplying by s plus sk whole squared both sides and putting s equal to minus sk, and b1, to find out b1 you will have to differentiate the function once. That must have been done while doing Laplace transform, right. This constant or these constants are called residues. All right. Now in our case we said if there is a pole on the j omega axis, suppose to be specific, let us say that our f of s is n of s divided by, let us consider a pair of poles on the j omega axis at plus minus j omega naught. That is, we have a factor s squared plus omega naught squared multiplied by d1 of s. Alright. Is the point clear? We have assumed the existence of a pair of poles at plus minus j omega. Therefore, I can expand this in this form, k0 divided by s plus j omega naught, one of the poles, plus s minus j omega naught, and from the discussion that I held yesterday, the residue here, the constant here must be complex conjugate of this constant. Why? Because the function is a real function. So, it would be k0 star plus other terms, okay, plus other the terms due to other poles. Now, if you combine these two, you assume that k0 is equal to k1 plus j k2, where k1 and k2 are real quantities. If k0 can be complex, you see our hypothesis, our statement was that if there is a simple pole on the j omega axis, the residue must be real and positive. Let us prove whether it should be real or not. Let us prove that it is real by contradiction. That is, if possible, let the residue be complex. Let the residue be complex. Then the sum of these two terms, that is T1 plus T2, the sum of these two terms, if you carry out the calculation, it is simply twice K1S. I think someone mentioned it yesterday. I hope he is right. Twice K1S minus K2 omega 0 divided by S squared plus omega naught squared. Agreed? The sum of these two terms. Okay. Now, if f of s is to be positive real, then its real part in the closed right half plane must be non-negative. That's correct. Its real part must be non-negative if real part of s is non-negative. Okay. Now, we do not have to test this over the complete right half plane. Let us test it on one particular axis, that is j omega axis. Let us see what the value is on the j omega axis. Let us call this as t. Then you notice that t, pardon me? No, there is a negative sign. There is a negative sign. It does not matter, even if it is positive sign, but it happens to be negative. Okay. Even if it is positive, it does not matter. Let us see. Let us see. So, what we said was, let us test at a particular, on a particular axis, j omega axis, for which sigma is equal to 0. The value of t j omega is twice k1 j omega minus k2 omega 0 divided by omega naught squared minus omega squared. Is that right? We have put s equal to j omega. And therefore, the real part of t j omega is equal to minus 2 k2 omega 0 divided by omega naught squared minus omega squared. Agreed? Because this is imaginary. This term k1 j omega is purely imaginary. Therefore, we ignore this. Now, you notice that when omega, if k2 is positive, when omega is less than omega 0, the value is negative, the real part becomes negative. Alright? If k2 is negative, then the denominator is negative for omega greater than omega 0. So, there exist values on the j omega axis at which the real part can be negative, and the only way that you can avoid it, real part being negative, is to make k2 equal to 0. Is the argument clear? That is the argument that I gave yesterday, but I did not carry out this calculation. Okay? Therefore, we prove that k0 has no other alternative but to become real. Alright? Now, if it is real, then the sum of these two terms, that is k0 divided by s plus j omega naught plus k0 divided by s minus j omega naught. Our next point of study is whether it is positive, whether it can be negative, because our contention was that the residue must be real and positive. Let us see, if it is negative, what harm? What is the harm? Again we will prove by contradiction. If you if you combine these two terms, it simply becomes 2 k0s divided by s squared plus omega naught squared. Alright. Now suppose the real part of this should be non-negative for real part of s non-negative. Okay. Let us test now not on the j omega axis but on the real axis, that is, let us assume let s be equal to sigma which is greater than 0. Alright. Then the real part of this, obviously the whole thing is real then, isn't that right? The function itself should be real. That's a part of the definition of a positive real function, and you see that the real part of this is equal to 2 k0 sigma divided by sigma squared plus omega naught squared. Now this is required to be non-negative because sigma has been assumed to be greater than 0. And what is the condition under which it can be non-negative? The only condition is that k0, because the denominator is positive, sigma squared plus omega naught squared, so k0 must be greater than 0. Can it be equal to 0? It can be. If k0 is 0, is there a pole at plus minus j omega naught? If k0 is 0, then there is no pole at plus minus j omega naught. Alright. Therefore, it need not bother us. There are infinite number of such poles in any given function for which the residue is 0. Right. So, our k0 must be strictly positive. Okay. So, we prove therefore that a positive real function.
Strictly positive, even if it is 0. then you don't have-
This is the point about which I made a pun. There are infinite number of such poles in any given function for which the residue is 0. If the residue is 0, it does not show at all. We are not concerned about it. Okay. For example, Divesh Pratap Singh is absent here. He is not present. Okay. We did not ask him a question because we know he is not there. Okay. So k0 cannot be 0. If it is 0, we don't bother about it. All right. Next one we say property number 4, that poles and zeros are either real or occur in complex conjugate pairs. Well, poles and zeros are either real or complex conjugate, and this is a property this is a consequence of the fact that the function itself should be real for S real. Okay, this we know. And then we said well, then we talked about two properties which we combine into one, that is the highest powers as well as the lowest powers in N and D cannot differ by more than unity. That is, the degrees of N and D can be equal, or at the most they can differ by 1. And the reason is that if they differ by more than 1, we shall have multiple poles either at the origin or at infinity, which is not permitted. And therefore, this property should be true, that the degrees of N and D and also the lowest powers in N and D cannot differ by more than 1. These are all properties, and I said they are all necessary properties, but they are not sufficient. For example, if you simply see that the degrees do not differ by more than 1, it does not guarantee that the function is pure. Okay? So, the question that arises is, what are the necessary and sufficient conditions? And obviously, you know one of the answers. What are the necessary and sufficient conditions? Well, if the function satisfies the definition, these are necessary and sufficient, all right? And therefore, necessary and sufficient conditions. Necessary and sufficient conditions. For a function f of s to be PR. And we assume that f of s is n of s by d of s. That is, it is a rational function. And one of the conditions is that the definition f of s real for S real and real part of f of s non-negative for real part of s non-negative. Now, if we want to test a given function to see whether it's positive real or not, the definition is difficult to apply, because this states that you shall have to explore all points in the right of plane, all points, all s in the right of plane, which is an extremely difficult task. That is, you have to put s equal to sigma plus g omega, consider all possible values of sigma and all possible values of omega. In very simple cases it may be possible, but not otherwise. So, what has been found out is people have worked on it throughout many years, and it was in 1939 a gentleman of German origin by the name Otto Bruni, B-R-U-N-E. He wrote a PhD thesis at MIT, Massachusetts Institute of Technology, which for the first time gave the testing procedure for positive real functions, a simpler one than investigating the total S plane. Yes, you have a question? No. When you point your pencil towards me, it's an indication that you are stuck. All right. So, Bruni said, well, it can be done in a simpler fashion. This condition, this is the difficult condition, because this is almost obvious. As soon as you look at the function, if there is a complex coefficient, you throw it out. Okay. Now, as far as this is concerned, he said, do three things. Number one, first find out if all poles are in the left half plane. That is, how do you find this? Not zeros. He says, take the function and test whether all poles are in the left half plane or not. Closed left half plane. How do you test that? You perform Harwitz test on d of s, on the denominator. Poles are the zeros of d of s. So, first question is you ask is d of s Harwitz? Is d of s Harwitz? Now, if it is Harwitz, that is, you divide the even part by the odd part, perform continued fraction expansion, look at the quotients, are they all positive? If they are all positive, then it is Harwitz. Okay. If it passes this test, then you ask the question, does the function have poles on the j omega axis? That, as I said earlier, will be discovered, if the function has poles on the j omega axis, it will be discovered during the Harwitz test. That is, it will end prematurely, and the last divisor shall have these factors. So, the next question you ask is, are there poles on the j omega axis? Okay. If the answer is yes, then you will have to test whether these are simple or multiple. Okay. If the answer is yes, if the answer is no, then you go to the next step. Okay. If the answer is yes, then you ask poles simple or multiple. If they are multiple, then your testing stops there, isn't it? Then the function cannot be pure. But if the poles are simple, simple poles on the j omega axis, then you test the residue, then you find out the residues. Then you find out the residues. How do you find the residues? You know that corresponding to a pair of poles at plus minus j omega naught, the term shall be 2 k0 s divided by s squared plus omega naught squared, right. So, how do you find k0? K0 is equal to, you multiply the given function by s squared plus omega naught squared. We do not want to handle complex numbers. We do not want to find out k0 by multiplying by s plus j omega naught and then putting s equal to minus j omega naught. Why? Because handling of complex numbers is more difficult than handling of real numbers. We can do by handling real numbers only because I can multiply by s squared plus omega naught squared and then divide by 2s, alright, and then put s squared equal to minus omega naught squared. That is correct. So that is how I can find out the residues. If there are simple poles on the j omega axis, then determine the residue and check whether the residue is real and non-negative. If it happens to be complex, then you stop testing. If it happens to be complex, okay, or if it happens to be negative, then also you stop testing. But if it is positive and real at all the poles on the j omega axis, not one, all of them, then you have to go to the next step, and the next step is the third step is to test the real part. All this does not absolve you from the responsibility of testing the real part. The real part has to be tested, but fortunately Bruni showed that you don't have to test the real part in the complete right half plane. You just have to test on the j omega axis. That is, the next part would be real part of f of j omega only on the j omega axis. Is it greater than 0 for all omega? If it is so, then the function is positive real. Now one might, because of the number of words that I used, one might think that this is more complicated than testing real part of f of s over the complete right half plane. That is not so, because these are mechanical and one can even program it on the computer, give the function and the computer will say whether it is positive real or not. One can write an algorithm, there are programs available. Okay. A couple of points on this testing. This testing, although it contains an infinite number of points from minus infinity to plus infinity on the j omega axis, the testing is in fact very simple, because if you recall we had done this, that if f of s, I want you to recall that if f of s is written as m1 plus n1 divided by m2 plus n2, where small m stands for the even part and small n stands for the odd part, alright, then you recall that by multiplying the numerator by the denominator and numerator, this is too light. If I multiply this by m2 minus n2 and this also by m2 minus n2, then I can break this up into its even part and odd part, and even part is m2 squared minus n2 squared. Do you see that this is even?
Yes.
Okay, and in the numerator I shall have m1 m2 minus n1 n2. This will be the even part, m1 m2 and the product of two odd parts n1 n2 plus the odd part which will be m2 squared minus n2 squared, and the numerator terms will be formed by n1 m2 minus n2 m1. Okay, this is the same thing, I have said it in an order. Okay, so this is the even part and this is the odd part. Why is it odd? Because the numerator is odd, the denominator is even. If both numerator and denominator are odd, then the function would have been even. Okay. Now our purpose is to find the real part of f of j omega. If I put s equal to j omega, in this, then you see that this would be purely real, isn't that right? It is an even polynomial divided by even polynomial. So the powers of s are s squared, s to the 4th, s to the 6th and so on. So this would be purely real and this would be purely imaginary. Okay. Therefore it follows that the real part of f of j omega is equal to m1 m2 minus n1 n2 divided by m2 squared minus n2 squared with s equal to j omega, and it is this function that we have to test. We have to see whether the question that we ask is this greater than equal to 0 for all omega. That is what we are asking, right. Given the function, I can identify m1, m2, n1, n2, I can form this and then test this, but this testing is further simplified by the fact that the denominator of this, that is m2 squared minus n2 squared, is m2 plus n2 times m2 minus n2, which is equal to the denominator of the given function d of s multiplied by d of, what is this in terms of d? D of minus s, not conjugate, no, not yet. This is d of s, then this is d of minus s, because if we change s to minus s, the only thing that changes is n2, the odd part changes its sign. Agreed? Okay. No, this point is not agreed? Okay. Therefore, m2 squared minus n2 squared under the condition s equal to j omega is simply equal to d of j omega multiplied by d of minus j omega. Now, these two terms are complex conjugates of each other. Agreed? Therefore, this is equal to magnitude d omega, j omega whole squared. One is the complex conjugate of the other, so the product of them is magnitude squared, and a magnitude squared is always greater than 0. Can it be equal to 0? Pardon me? Can we permit magnitude d j omega squared equal to 0? Then the real part is infinity. So the function does not exist. Alright. So it is strictly greater than 0. If it is greater than 0, then obviously we do not have to test the denominator. We only have to test the numerator. Agree? Is this point clear? This is a rational function, real part of f of j omega. There is a numerator which is an even polynomial in omega. There is a denominator which is an even polynomial in omega. And we prove that the denominator polynomial is always positive. If that is so, all that we have to test is only this part. That is, we have to test m1 m2 minus n1 n2 under the condition s equal to j omega. Now, would you like to put s equal to j omega in this to find out what this is, or would you like to evaluate it in some other fashion? I have already given you the clue. We do not like handling complex numbers, right, because they create complexity. By definition, complex numbers have to be complex, isn't it? There is no other way, they cannot be simple, and handling of complex number is going to be complex. But you notice that m1 m2 minus n1 n2 does not contain any odd power of s, they all contain even power. So we could as well, instead of this, we could as well put s squared equal to minus omega squared, and therefore this polynomial, this will now be a polynomial, it would be a polynomial in omega squared, a of omega squared. Alright, is that point clear? And the question that we have to ask now is this greater than equal to 0 for all omega? Now further simplification. You see, we do not have to test for all omega, because only positive values or only negative values. Okay. So we say no, we will not test for all omega, we will only test for omega greater than equal to 0. But let us avoid that question also, because it is a function of omega squared, because it is an even polynomial. Why don't we simplify by saying no, we won't test a of omega squared, we would put omega squared equal to some other variable, let us say x, alright, and test. How do I find a of x? I take m1 m2 minus n1 n2 and put s squared equal to minus x, and then test. What do I test? Is this greater than equal to 0 for x greater than equal to 0. Done? This is the lowest form, we cannot simplify it further. A of x will now be a polynomial in x. In x it is neither purely even nor purely odd, but we have to test only for x greater than equal to 0. That does the job. Alright. So, it would be of the form a0 plus a1x plus etc. plus let us say a n s to the n. I am sorry, x to the n. Okay. So, this is the polynomial that you will have to test. You see, from the real part of z of s non-negative for all values of s in the right half plane, we have come a long way. Only thing we had to check is whether the denominator polynomial was Harwitz or not. And then we had to test, if it is Harwitz, does it have poles on the j omega axis? If so, are these poles simple? If these are simple poles, are the residues real and positive? If all the questions are answered in the affirmative, then we come directly to this polynomial, capital A of x. Okay? A long way. Before we subject this to further test, let me ask a question. Suppose in this polynomial, suppose we discover that there is a factor like x minus alpha. Suppose I discover that there is a factor x minus alpha, where alpha is positive. What conclusion can we make? The function, original function was not pure. Because if x, the original function was not pure, this is jumping many barricades. Because if there is a factor x minus alpha where alpha is greater than 0, then for some values of x this will be negative, isn't that right? X equal to 0 for example, it will be negative. Is the point clear?
Yes, let's say the function would come down and go up again.
Ah.
Like x squared. For example.
Okay, x minus 1 multiplied by a polynomial which has no negative powers. Okay. Obviously, for x less than 1, the function will be negative. Isn't that right? For example, let the other powers be x square plus 3x plus 5, let us say. Obviously, if we have a factor like this, then we do not have to proceed further. If we can discover that there is a factor like this, then we do not have to proceed further. But suppose it is x plus 1, then we need not worry. Agree? Then we will have to check the rest of the polynomial. Okay. But there is an exception. Suppose the power, suppose x minus 1 is not just one root, but there is a double root. Then we need not worry, because squared cannot be negative. Similarly, it is not just 2, it could be twice p, where p is any integer. Agree? In other words, if we discover that there are even number of roots on the real axis, okay, x equal to 1 is a point here. If there are even roots here, then what will happen is a of x will go like this, it will go through 0 and then go like this. But if it is odd, if the power of x minus 1 is odd, that is 1 or 3 or 5 or 7, then what it means is that if this is the point, the polynomial goes through a change of sign. Is that clear? The point clear? This is one of the observations that we make. Sometimes it is possible to discover whether, just by observation, it is possible to discover whether a of x is non-negative or not. But enough of theory, let us work out some simple problems. Pardon me? This point? Okay, if we discover that a of x has a factor x minus 1 with a power of 2p, then obviously this factor will not give rise to a negative value, because x minus 1, even if it is negative, raised to an even power is always positive. On the other hand, if it is 2p plus 1, then obviously at x equal to 1 there is a change of sign. It remains positive, then becomes negative. Sometimes it is useful. But let us look at some graded problems, some problems of graded difficulty. Let us say that we have a function f of s equal to s plus a divided by s squared plus bs plus c. obviously the first thing that you look for is, we have to test this, that is we ask the question, is this PR? Okay, or let us say what are the conditions? I think that is a better way. Under what conditions is this function f of s PR? Okay, under what conditions? The first thing we say is that a, b and c should be real and real and not necessarily non-negative. Isn't that right? Some of them, one of them can be 0. Why not? Non-negative. For example, if a can be 0 here, even then the function could be positive real. So you must allow this. Not all powers have to be present. The numerator could be simply, you see, all that we need is that the numerator and denominator degree should not differ by more than 1, and therefore a could be equal to 0.
But if B and C are 0,
If b and c are 0,
then there are multiple poles
then there are multiple poles
at
at the origin, and therefore the function would be. So that is one of the restrictions, that b and c cannot be simultaneously 0. We will come to all this. We will come to all this. Yes. Can b be 0? A and c are not 0. B can be 0? Okay. B, if b equal to 0, then are there any restrictions on A and C? Yeah.
So can't we have these as negative?
Can we have A, B and C as negative?
So if two of these cancel each other, say s minus
What can cancel?
So s minus 2 suppose, and there is also s minus 2.
No, please reflect this. Can B be negative? If B is negative, obviously this polynomial will not be Harwitz. If C is negative, obviously this polynomial will not be Harwitz. If B and C are both negative, then also it is not Harwitz. Right? So there is no other alternative. We are being biased toward negative quantities. We are being negative towards negative quantities, but there is no alternative, because we are talking of positive real functions, definitely positive. Positive numbers are our bias. Okay. If b is 0, does it put a constraint on other constants? You see, let us look at this. That is what I said, some fun. If b is 0, then f of s can be written as s by s square plus c plus a by s square plus c.
A is positively.
It turns out, yes, a is positive real. No, your statement turns out to be wrong. Let us see. Suppose we want to test on the j omega axis, f of j omega. Then you notice that this quantity, the first term, shall be purely imaginary, and therefore the real part of f of j omega is a divided by c minus omega squared, which can be negative.
Yes, sir.
Therefore the only condition that the condition that has to be satisfied is that a should be equal to 0. So if b equal to 0, then a must be equal to 0. Okay. Suppose b is not 0. Is this point clear?
Yes, sir.
If b is 0, then a must be equal to 0. That is, the factor would be, the function would be of the form s by s squared plus c. Yes, that is positive. Yes. Okay. Now let us see in general. If b is not equal to 0, do we have to test the multiplicity of poles on the j omega axis? No, there can be only one pair. If b is 0, then s square plus c. These are simple poles. And what is the residue then?
S square plus C.
No. Our function is, let me ask the question again. Be careful about what I am asking. B is 0, and we have shown that if b is 0, then a is also 0. So what is the function then? S by s square plus c. It has a pair of poles on the j omega axis. These are simple poles. What is the residue?
A minus C.
That is the correct answer. You see,
Half A minus.
because it should be of the form twice k0 s divided by s squared plus omega naught squared. Obviously the poles are at j square root c, and k0 obviously is equal to half. That is the correct statement. Alright. But suppose b is not equal to 0. Our function is s by a s square plus bs plus c. B is not equal to 0. If that is so, then we go right away to the real part testing. That is, we test a of x, which is, with some experience you will be able to do it instantly, which is m1. What is m1? A. m2 c plus s squared, m1 m2, minus n1 n2, that is s times bs, under the condition s squared equal to minus x. Don't forget this. So this is a c minus x plus bx, that is equal to ac plus b minus a times x. And if this has to be greater than equal to 0, for x greater than equal to 0, obviously the condition is that b must be greater than or equal to a. Right? You see, AC is a positive quantity. If this is the only quantity which can lead to negative signs, and negative signs can occur only if b is less than a, and therefore in order that this remains non-negative, we must have b greater than equal to a. This also shows that if b is 0, then a has no other alternative but to comply with b. It has to follow b. It has to be also equal to 0. Alright, let us take another function. Now, concrete examples. S squared plus 4s plus 2. Is this PR? Just by looking at it, it is PR. Suppose I have s plus 2 divided by s squared plus s plus 2. Yes? No, non-PR. I have s plus 1 divided by s squared plus 2.
It is.
No,
It is.
because b is 0 and a is non-zero. Now, we in the remaining time, let's complicate the function. That is, we have f of s equal to a general biquadratic, s squared plus a1s plus a0 divided by s squared plus b1s plus b0. Now, the numerator has been made into a quadratic. In the previous case, the numerator was linear and the denominator was a quadratic. We asked the question, what are the conditions, under what conditions is this PR? You see, the first thing we say is that a0, a1, b1, b0, they must be real and non-negative, not strictly positive. Some of them can be 0, but you have to be careful which one can be 0, which one cannot be. Suppose b1 is 0, under this condition, what are the constraints on a1, a0 and b0? Well, if b1 is 0, obviously we shall have poles on the j omega axis, and these poles are simple, right? Either at plus j square root b naught or minus j square root b naught. And the residues there, how do you find the residues? If b1 is 0, what are the residues? What is the residue at the complex pole? At the imaginary axis pole? What is the residue? A thing is obvious when you see it. Why don't you see it? What is the question? If b1 is 0, we have a pair of poles on the j omega axis. What is the residue there? That is the question. As simple as that. Alright, I will leave you with this question.
B0 square minus A1 B0.
Is it a1 by 2 by any chance? you can show that it is A1 by 2.
2 cannot as equal
Pardon me?
to, the 2 cannot as equal to A1 is.
That's right, therefore cannot is A1 by 2. It should be obvious, but there is a condition. It's not that obvious. Okay? The condition, for finding out that condition, we'll have to test A of x. Well, what is A of x? Can I write without going to S squared? Can I write this as A0 minus x multiplied by B0 minus x plus A1 B1 x? Can I write like this? Directly? With a little experience you will be able to do that. Okay. And what we want to do is, we ask the question, is this greater than equal to 0 for x greater than equal to 0? We shall look at this carefully next time. The textbook makes a mess of this testing. I will give you a very simplified procedure. Okay? Next time.